Hello and welcome to this presentation on the design of a reversible pump turbine for retrofitting of existing hydropower plants. My name is Carl Escher and this project has been supervised by N Dagsvik and T S Storli. While a regular hydropower plant only is able to deliver energy to the grid as a turbine, a pumped hydropower plant will be able to extract energy from the grid as well in pump mode and use this energy to pump water up to the higher reservoir. So the pumped hydropower plant will pump water up if there is too much energy in the grid and the energy is cheap, and run as a turbine when there is too little energy and energy is at a high price. So it kind of works like a battery. Because constructing an entirely new hydropower plant is expensive, we want to look at the possibilities of reusing an already existing hydropower plant with a Francis runner installed and to replace that runner with a reversible pump turbine, a so-called RPT. So it should be capable of both pump and turbine operation. So we want to keep the dimensions of the draft tube and of the guide vanes constant, and we only want to replace the runner itself. We also want to keep the volumetric flow rate and the lifting height or head of the pump or turbine, and the rotational speed of the current arrangement. There are a couple of challenges affiliated with doing this. One are the pressure losses in the system. This curve here represents the pressure losses in turbine mode. The pressure decreases steadily in the penstock from the higher reservoir through the penstock and to the reversible pump turbine. Then there is a sharp decrease in pressure through the turbine, because that is how we actually get energy from the system. We transform pressure to movement to electricity in the turbine. And then the pressure decreases further through the draft tube and to the lower reservoir. In pump mode, the flow goes in the other direction, so therefore it decreases from the lower reservoir to the pump. Then there's a sharp increase in the pump, and then it decreases again through the penstock until it reaches the higher reservoir. Due to this, there are pressure differences upstream of the RPT, the reversible pump turbine, and downstream of the reversible pump turbine, those here. To understand what these pressure differences have to say for the design of the RPT, we will have to take one step back and take a look at Euler's pump and turbine equations. These equations relate the power of the pump to the velocities of the runner and the velocity of the fluid, but projected onto the same direction as the runner velocity, Cu1p, at location 1, which here is along this line right here, and at location 2, which is this line here, and the efficiency of the pump, and relate this again to the lift-in height of the pump, or the pressure produced, because height can be expressed as meters of equivalent water column. The same goes for the Euler turbine equation, which again relates those properties to the pressure upstream of the turbine, or the height upstream of the turbine, the pressure height, so-called head. Because the pressure of the pump is larger than the pressure of the turbine, this means that CU1 for the pump has to be larger than CU1 for the turbine, which again means that the blade angle of the pump has to be larger than the blade angle at the turbine at best efficiency point. Another challenge occurring when designing pumps is a phenomena called slip. Slip occurs because there is a high pressure area at the pressure side of the blade and a low pressure area at the suction side of the blade. Therefore, the outgoing flow will be deflected from following the exact angle of the blade to being pushed towards the low pressure side. And thus the angle of the outgoing flow will be lower than the blade angle, which further amplifies the previously mentioned problems related to different blade angles of the pump and the turbine and the flow angles related to those. Another challenge is the influence of streamlines and the influence of the pressure gradient on the behavior of the streamlines. So while the flow goes from high pressure to low pressure, there is usually not a problem. The flow stays nice and attached and follows the geometry quite closely. But when there is a low pressure here and the pressure increases in the same direction as the flow goes, this will lead to detachment of the streamlines and vortices and separation, and this again leads to hydraulic losses and lots of stuff we really don't want in our pump turbine. So the reason why this becomes a problem for us is that the area at 1, the meridional area at 1, is larger than the cross-sectional area at 2. So large area means small velocity due to continuity equation, which again means large pressure due to Bernoulli's equation. And vice versa, small area means large velocity, means small or low pressure. In turbine mode this is fine. The flow will go from a high pressure area to a low pressure area. The flow will most likely remain attached, but in pumping operation the flow will go from low pressure to high pressure, which is exactly this situation that we want to avoid, and that is a problem. Yet another challenge is the occurrence of cavitation, which occurs due to the large pressure difference between the pump mode and the turbine mode, and because the system is designed for turbine operation. This will hopefully be resolved by the installation of a booster pump downstream of the turbine, which may increase the pressure on the turbine. If you're interested in this project, you should take a look at Ingrid Befring-Hage's project. She has also submitted her work to this conference. So how was this RPT designed? First of all, I prioritized the good operation conditions for a pump over the ones for a turbine. This is because a radial pump, which is set in reverse to work as a turbine, will always be able to generate at least some power, while a turbine, which is reversed and is supposed to create pressure, is not necessarily able to create sufficient head to pump the water all the way from the lower reservoir to the higher reservoir. Therefore, the design of a pump was prioritized. That's why obtaining sufficient head is of prior concern to me. Now, because of the given dimensions, the U1 cannot be changed, and thus the only thing I can change to produce more head, according to Euler's pump equation is Cu1, which is increased when increasing the value of beta 1. Beta 1b is the blade angle and beta 1 prime is the angle with slip. To find the value of beta 1, which is required, I use this formula here, which is a variation of the Euler pump equation, together with models for the efficiency of the pump and a model for the slip angle, together with measured values of the pressure loss in the system as it is today. And I found a point where the delivered head by the pump is larger than the required head by the system at volume flow rate of 51 cubic meters per second. Now with the beta 1 value known, the blade had to be shaped in 3 dimensions. Remember, we want to reuse the existing geometry. So I started with defining the meridional projection. Here we have the following points fixed. The guide vanes, we want to reuse the guide vanes, so their position at the hub and shroud are fixed. The runner starts at these points. This is where it transitions from the concrete part of the building itself to the runner, which we are allowed to change. And we know the dimensions of the draft tube, so we also know their placement at the shroud and hub. Now to find the shape of the hub, I used a Bezier curve, which is a curve which is everywhere smooth, among other properties. And I used 3 control points, one at the inlet, one at the outlet, and a third one, which I increased and iterated until the curve itself hit the midpoint, which is indicated here, which is the same as this one. Then I found a streamline for the shroud by iterating downwards from the hub, assuming a variation of the cross-sectional area, which was continuously varying and smooth everywhere. By doing this, I eventually found a streamline for the shroud. Now the thing is that the shroud also has to pass through 3 points, and to do this I had to vary how the variation in area from the inlet to the outlet varies, again using a Bezier curve, until also the shroud, indicated in this line here, passes through the control point at the inlet, at the midpoint, and at the outlet. So with the meridional view known, we can now define 2 new variables. One is the G variable, which is the length of the line from the inlet, where it is 0 at the inlet and at its maximum at the outlet. And the H value, which is the length of a line but in the R theta view and not in the meridional ZR view. So the G values are known for each and every point, because we know both the Z and the R values, but the H values are still unknown because we don't know how much the blade changes in the theta direction for each new point. In other words, we don't know the values of beta along the blade yet. Therefore, we have to obtain the blade loading or the distribution of beta along the blade. One way of doing this is to apply a UCU distribution, which is, if you look at the Euler pump equation, you can see that how much power is transferred to a blade depends on the change in U times Cu at one point and U times Cu at another point. Therefore, if we control this change of U times CO2 along the blade, it allows us to control where power is transferred to the blade. In a pump turbine, we want this curve to be flat, close to the inlet or the outlet in pump mode, because we there want to have small energy changes to decrease the pressure difference between the pressure side and suction side, to again decrease slip losses. And then we want it to be steep in the middle part and flat close to the outlet again. Another way of doing this is to just choose a variation of beta from the beta 1 value, which we found earlier, and to the beta 2 value, which also easily can be found. And just, for example, assume a Bezier curvic variation there as well. After all of the beta values for all of the points had been found, and thus the R, Z, and theta values of every point had been found, the results were inserted into programs for computational fluid dynamics, CFD, which basically discretize and simplify the Navier-Stokes equations and other fluid mechanic equations, and solve these numerically to obtain approximate solutions. So to begin with, I tried to create the blade using the UCU distribution. The distribution looked like this, and created a blade looking like that. Now this is not what I hope to obtain, because we have sudden changes in the blade along the blade, and that is typically a cause to which creates separation of the flow. And sure enough, looking at the results from the CFD simulation, we see that there is separation in the pressure side of the blade. The blade produced a lifting height of 47 meters water column, which is definitely not enough to meet the requirements of the system as it is. After that utter fiasco, I decided to go with the smooth beta variation instead. It looked like this, where the beta 1 is at 0 G and beta 2 is at 1 G divided by G max, and it varies smoothly between the two extreme points. The blade looked like this, which is a much more reasonable shape for a blade, I would say, because it is much smoother and uniformly varying. This was confirmed by the computational fluid dynamics, which show us that the flow stays quite attached at low values along the z-axis. But unfortunately, we again get separation at high values along the z-axis, so far away from the draft tube. This is due to the variation in area, as explained earlier, and was something to be assumed would happen. Unfortunately, this blade only delivers 48 meters of water column, which is 1 measly meter more than the last blade using the UCU distribution. And it is far away from the target value of 83 meters, or maybe 73 if the booster pump delivers 10 meters of lifting height. So obviously there's a lot of improvement potential here. I should find a good method to distribute the beta values along the blades. I should consider if I could make other changes to the runner, which will increase the head. If I at some point get high enough head, the turbine should be tested as a turbine as well and simulated together with the booster pump. And lastly, a prototype of the RPT should be made and tested with real fluids to make sure that the solutions obtained from the CFD are to be trusted. Thank you for your attention.